So, using the assumptions of the kinetic molecular theory, which describes how ideal gases behave, and some basic physics, we can find this equation for the pressure of an ideal gas. So here the N is the moles of gas we have. The big N with the A on the bottom is Avogadro's number, 6.022 times 10 to the 23rd. And then m is the mass of a single particle. And the u squared with the bar over it is the average of the square of the velocities of each particle. So you take the velocities of all the particles, square them, and then find the average, and that's this number. And we don't use a v because it'll get mixed up with the volume on the bottom. So if you're in physics, you know that the kinetic energy of a particle is 1/2 mv squared. And so this expression, 1/2 mu squared, is the average kinetic energy of a single particle. And so if we multiply it by Avogadro's number, then we'll get the average kinetic energy for a whole mole of particles. And so then we can rewrite the equation for pressure like this, using the fact that Avogadro's number times 1/2 mu squared is the average kinetic energy of a mole of gas particles. So then we can rearrange this to get PV over N equals 2/3 times the kinetic energy. And remember, in the kinetic molecular theory, one of the assumptions was that the temperature of a gas is directly proportional to the average kinetic energy. So we can write 2/3 kinetic energy average is proportional to the temperature. And since this equals PV over N, we found that over here, we can also write PV over N is proportional to the temperature. And so if we take the proportionality constant as the universal gas constant, so then we get PV over N equals T. That's just the ideal gas law. So the whole point is that the ideal gas law was first formed through experiments, but using the assumptions of kinetic molecular theory and physics, we can derive the ideal gas law just from doing some math. So also from these equations, we can see that the Kelvin temperature is just a measure of the particle's average kinetic energy, or their random motion. Because, see, if we take the constant of proportionality here as the universal gas constant, then we can write the kinetic energy, the average kinetic energy of the particles is equal to 3/2 T. And we can also define the root mean square speed as the square root of this average velocity squares. So since the kinetic energy is equal to Avogadro's number times 1/2 mu squared, we found that earlier. And we also found that the average kinetic energy is equal to 3/2 times T. If we set these equal to each other, we can solve for the average u squared. And then if we take the square root of both sides, that'll be the root mean square speed. And then we can simplify it further, because the m is the mass of a single particle in kilograms, because we use kilograms in physics. And so if we multiply the mass of each particle times Avogadro's number, that's the mass of a mole, or the molar mass, but it's in kilograms, not grams. So in all, we get the root mean square speed is equal to the square root of 3T over the big M, which is the molar mass in kilograms. And so here we can't use the 0.0821 value of we need to use this 8.314. And it's because of how the units work out. So for example, we can find the root mean square speed of helium gas at 25 degrees Celsius. So all we have to do is find the Kelvin temperature, and then we know the universal gas constant with 8.314 instead of 0.0821. And then the molar mass of helium is 4 grams per mole. So in kilograms, it's just 4 times 10 to the negative third kilograms per mole. So we plug those into the expression for root mean square speed, and we solve and get 1.36 times 10 to the third meters per second. So you can see that the gas particles are moving pretty fast on average. But in any gas sample, all the particles are not moving at this speed. This is just the average. The velocities of all the particles will have a wide range because they're just bouncing around randomly. So they can randomly speed up or slow down when they bump into something. So we can represent the distribution of the velocities with it's called a Maxwell-Boltzmann distribution. So it shows the probability of any particle having a certain velocity. So here you can see the graph. On the x-axis is the velocity, and on the y-axis is the probability of a particle having that velocity. So at the peaks of these graphs is where most of the most likely velocity. So if we just pick a random particle from a gas, it'll most likely have a velocity around the peak. And we also have 3 different graphs at different temperatures, and you can see as the temperature increases, the peak moves to the right because the particles are more likely to have a higher velocity since they're moving faster at higher temperatures.